An atom is the smallest unit of matter that retains all the chemical properties of an element. What this means is that if I have an atom of gold, it is distinctly gold, and it is different than an atom of carbon or helium or silicon or magnesium. And while we can break that atom into smaller pieces, which we call subatomic particles, once we break open that atom, it no longer has the distinct properties of that element. All protons, all neutrons, and all electrons are the same as any neutrons, protons, electrons in any other atom. It is their arrangement within the atom that gives that element its distinct chemical properties. An atom consists of two regions. First, there's the tiny, dense, super small atomic nucleus, which is in the center of the atom and contains the positively charged particles called protons and neutral uncharged particles called neutrons. The second region of an atom is the electron cloud. This is the area outside the nucleus, and while it takes up most of the space of an atom, it has almost no mass. It is mostly empty space, but it's a cloud of negatively charged particles called electrons that surround the nucleus. It's this attraction between the positively charged protons and the negatively charged electrons outside the nucleus that hold the atom together. So to recap, the protons, which are positive, and the neutrons, which are neutral, make up the nucleus of an atom. The nucleus has an overall positive charge since it contains only the positively charged protons and the neutrons, which again have no charge. Interestingly, the nucleus makes up less than 0.01% of the atom, but it is more than 99.9% of the atom's mass since it contains the heavy subatomic particles, protons and neutrons, which each have a mass of approximately 1 AMU, which stands for atomic mass unit. I was once told that if you were to blow up the size of an atom to equal maybe Citizens Bank Park, where the Phillies are winning the World Series right now, the nucleus would be merely the size of a tiny marble sitting on second base, where the electron cloud would fill the space of the entire stadium. This gives you a magnitude of how small this nucleus is compared to the size of the atom being the whole stadium. Atoms of every element have a specific number of protons, and this number of protons, which are in the nucleus, is called the atomic number. This determines what element the atom is. If you look at your reference table, this atomic number is actually the number in the top left corner of your periodic table. For example, the atomic number for sodium is 11. Let's take a moment to get used to your periodic table. I want you to fill in the blanks with the missing element name, symbol, atomic number, and number of protons for each of these options below. Remember, the atomic number and the number of protons are always the same number. I'll pause for a moment to let you try this now. And here's what your table should look like. Pause the video right now to double check your work. John Dalton in his atomic theory said all atoms of a given element are identical by mass and other chemical properties. But he was wrong. Not every atom of a given element is identical. But every atom of a given element must have the same number of protons, which again we know is defined by the atomic number on your periodic table. But atoms of a given element can differ by the number of neutrons in the nucleus. And since the protons and neutrons are what provide the mass of the atom, this means that atoms of the same element can have different masses. Atoms of the same element with different masses are called isotopes. So how do we distinguish between two atoms of the same element that have different masses? Well, we include a number called the mass number, which the mass number of an atom is the sum of the protons and neutrons in the nucleus. Since atoms of the same element can have different masses, it's often useful to use the isotope notation and isotope name when referring to a specific isotope of a given element. Isotope notation looks like the format below. Note, this is not the format on your periodic table. I know it looks similar because it's a box with the letters and the numbers and everything looks kind of similar, but it's not. This notation only refers to one specific isotope of a given element. The periodic table is an average of all the isotopes of that element. So while some of the numbers are similar, some of the numbers are very different, and that can be confusing. Isotope notation has the atomic number in the bottom left-hand corner, and the mass number, which is the sum of the protons and the neutrons in that specific isotope, that goes in the top left-hand corner. It still has the element symbol in the middle of the box. When we write the specific isotope name, we name the element, which is based off of the number of protons. All carbon, every isotope of carbon has 6 protons, and this isotope has 6 protons, so we call it carbon. But what we need to do is we need to add a tag to tell us how heavy this specific isotope of carbon is. This carbon is carbon-14. And since we know that the mass number is the sum of protons and neutrons, then we can calculate that that means that this carbon has 8 neutrons. Take a moment to try to practice this. We'll do the first one together. First, let's focus on the fact that if you know the name of an element, if you know the symbol of the element, if you know the atomic number of an element, or if you know the number of protons, if you know any of those 4 things, you know all 4 of those things, because the atomic number and the protons determine the name, and the name determines the symbol. So if you know one, you know all 4 of those things. So for this first example, we know the element name is chlorine. We look at the periodic table, we see that chlorine is the 17th element on the periodic table, which means it must have 17 protons, and it has the symbol of a C with a lowercase l. The next bit, the mass number, tells us the number of neutrons, because neutrons plus protons give us mass number. So in the case of this chlorine 37, 37 is the mass number. And once we know the mass number, we know that protons plus neutrons equal mass number, so the neutrons must be 20. Pause the video and attempt to fill in the rest of the table on your own. I'll give you a moment, and then you can check the answers. Okay, so this is what you should have gotten. I really want to stress the fact that we have different versions of the same element. 2 versions of chlorine, which are different by their mass. 2 versions of lithium, which are different by their mass. 2 versions of hydrogen, which are different by their mass. But every element, its partner or its isotope, has the same number of protons as every other atom of that element. A given element can only differ by their number of neutrons and therefore their mass. Remember that the notation on the periodic table is different than isotope notation, and individual isotopes are not reported on the periodic table. The mass on the periodic table is not the mass number. It's actually something called the average atomic mass. This average atomic mass is actually an average of all the stable isotopes of that element that we find in nature. So for the case of magnesium, there are 3 common isotopes of magnesium. Magnesium 24, which has a mass number of 24, magnesium 25, which has a mass number of 25, and magnesium 26, which has a mass number of 26. However, you look at the periodic table, and the average atomic mass reported on the periodic table is none of those. It's not 24, it's not 25, nor is it 26. The average atomic mass is 24.31. Well, you may be thinking the average of 24, 25, and 26 is 25. So why are we reporting the average mass of 24.31? And that's because not all 3 isotopes are found equally in nature. We have a lot more of magnesium 24 in nature, so that skews the average towards the mass of 24. This average mass on the periodic table is a weighted average, meaning you have to take in the percentages of each isotope into the calculation. How we calculate the average atomic mass is actually kind of simple. We take the mass of the individual isotope and we multiply it by its abundance in nature. And then we just sum each mass times its abundance. Let me give you an example. First of all, mathematically, when you have a percentage, it's usually easier to use that in a calculation in its decimal version. So each of these percentages, we're just going to go ahead and divide by 100 to get the decimal equivalent, because a percent is a per 100. So we're going to divide it by 100 to remove the percentage. Then we're going to take each isotope's mass and multiply it by its decimal abundance. Once we get the product of that mass times the abundance, we just sum that for the 3 isotopes found in nature. And when we sum these 3 values, we're going to see that our average atomic mass for magnesium is exactly what it says on the periodic table, 24.31. Now let's practice your skills at calculating average atomic mass. Turn the page and practice with your partners. We've talked a lot about what's going on in the nucleus of the atom, but now let's talk about outside the nucleus, the electron cloud. Neutral atoms have an equal number of the positive protons in the nucleus as they do negative electrons surrounding the nucleus. And while the protons can never change in an atom, in chemical reactions, electrons can be lost, they can be gained, or they can be shared. We'll talk more about sharing electrons later, but let's focus on electrons being lost or gained and what it does to the actual atom. When a neutral atom gains or loses electrons, the protons and electrons are no longer equal to one another. This unbalance of charged particles makes the atom become a charged ion. When an atom loses electrons, there will be less of the negative electrons than there are positive protons in the nucleus. This results in a positively charged ion called a cation. Meow. Cations are positive. However, when an atom gains electrons, there will be more negative electrons than there are positive protons in the nucleus. This results in a negatively charged ion called an anion. I don't have a cute mnemonic for that. When an atom gains a charge and becomes an ion, we can actually add that to the isotope notation in the top right-hand corner. This charge is the difference between the protons and electrons in the atom. If it is a positive 2 charge, that means you have 2 additional positive particles, right? The difference between electrons and protons is that you have 2 extra positive. We see here with the neutral atom, there's no charge listed. That means there's no difference. So protons and electrons are equal to each other. This has no impact on the number of neutrons and the mass number. Now we're going to try to put it all together into one giant table and count up all the subatomic particles of an atom. Let's remind ourselves which of these categories are dependent on each other. So again, the name, the symbol, the atomic number, and the number of protons. If you know one of those values, you know all 4 of them. If you have protons plus neutrons, that gives you the mass number. And then the difference between protons and electrons give you the charge. So the protons are kind of the key to unlocking all of this information. Doing this first one together, we see that the number of protons are 6. So that immediately tells us we're dealing with the element carbon. The symbol is C, and the atomic number is 6. Now that we have all that information filled in, we know that protons plus neutrons equals mass number, so we must be dealing with the isotope of carbon that is carbon number 12, mass number 12. And since the protons and electrons are equal to each other in here, there's no difference, so the charge is 0. We have a neutral atom. Pause the video and try to fill out the rest of the table on your own, and I'll show you the answers in a moment. Okay, so this is what you should have.